Hello everyone, this is Miss Salter and I am going to summarize heat of fusion and heat of vaporization and how to kind of do combo problems with both phase changes and temperature changes following our phase diagram. So, we watched a video on heat of fusion, heat of vaporization. These are both used in phase changes. We are changing from a solid to a liquid to a gas, or backward from a gas to a liquid, and a liquid to a solid. So these are the two equations we have. This one, Q equals M, um, the heat of fusion is for melting and freezing. And then Q equals mass times the heat of vaporization is for boiling and condensing. They're different for each substance. These are two numbers that are different for depending on what substance you're talking about in the problem. Most of our problems are going to deal with water, so that's not too big a deal. Okay. So if we scroll down here, and for some odd reason, oops, we went too far. Hang on a second. Okay, so we're looking at this diagram for water. This should look kind of familiar. You should already have one of these in your notes. I color coded this one so that we can see kind of what we're referring to. So the sloped parts are where we have just a temperature change. The phase of the substance has not changed. It is going to be either a solid, a liquid, or a gas. The temperature here on this chart is for water. So if we are moving in a temperature that does not go lower than 0 and does not go higher than 100 degrees Celsius, then we are dealing with liquid water the entire time, and therefore we have just a temperature change. Now, when you are working within each of these sloped areas, you have when you are working with a temperature change, you're working just in that temperature range. And we'll see how that applies later on during one of the examples. The plateaus, the yellow and the pink, are when we are actually doing a phase change. That's when we're using our heat of fusion or heat of vaporization, and we're using Q equals M times one of those two constants. That's where we are either melting or boiling, or we are condensing and freezing, depending on what temperature we're at. The temperature during the phase change stays the same. It is 0 degrees Celsius, it is 100 degrees Celsius, depending on which phase change we are talking about. If the arrow is going to the left, it's exothermic. If it is going to the right, it is endothermic. So if it's going to the right, we are absorbing energy into our substance. If it's going to the left, if our little arrow there on the phase diagram is going to the left, then that means that we are giving off energy. Okay, a little weird that way, but that's what that refers to. So down here at the bottom, I just have as the temperature rises or falls, you follow the curve to know how to break the problem into parts. If you were watching the example in the previous video that we saw, if the temperature goes, say, it starts at, let's see, if our temperature starts, say, here, and it goes to here, And so that means the temperature goes up, then we have a phase change, and it goes up a little bit more. Then we're breaking that into 3 chunks. We have to do 1 chunk here, 1 chunk here, and that's supposed to go all the way to the end of the pink, and there. Okay, so that's what that is all about. So, going down here, let's see. Exothermic processes, or if the temperature is falling, will result in a negative value. We have an energy release because our values for heat of fusion, heat of vaporization, or our change in temperature are all negative. It's kind of one of those weird things where the negative value doesn't mean, it just means that we're releasing energy. The energy value, whether we are, say, freezing or melting, remains the same. It's just if we have a negative value, we know that we're freezing because we are giving off energy rather than absorbing energy. Next page. So here's a little 3 little easy kind of summary statements for you. We use Q equals MC change in temperature if the temperature is rising or excuse me. If the temperature is rising or falling, then we are dealing with just one phase. It's a liquid, or it's a solid, or the substance is a gas, but we are not changing phases. The other 2 are for when we are changing phases. And like I have there, if it's going from a gas to a liquid or a liquid to a solid, then it's going to have a negative value. So we're going to see how we use that as we go through these example problems. So first problem, if 75 grams of water is boiled completely, the heat of vaporization of water is 2,260 joules per gram. How many joules of energy is used? Now, this means that we have our liquid water is at 100 degrees. Our steam afterward, or our gaseous water, is at 100 degrees. We are just talking about the pink part in the middle. And you see how I have these all color-coded for you? So you can go back up here to the phase diagram and see what part I am referring to. Okay? Tried to get it simple for you guys because it's a lot to talk about at once. We are using our plan system. It seemed to work really well in reaction conversions. I'm sticking with this a little bit just so that we can get some continuity going on between all of these problems. So our plan is we are going from water in a liquid to water in a gas. So it's a phase change. We're using our equation Q equals M, heat of vaporization, because we are vaporizing the water. We are putting it into a gas. We're making steam. I just rewrote my givens there, our mass and our constant. We're going to plug those in, do the math, get the answer, got it boxed. Okay. Next one is also a phase change. Here, though, we're not using water, we're using copper. If we use some other substance, I will give you all of the relevant information in the problem. This one is a little bit weird because this one, if we are using 1675 joules of energy are used to melt 12.5 grams of copper, what is the heat of fusion of copper in joules per gram? We are looking for our heat of fusion here. So our plan is we're going from solid copper to liquid copper. We are melting it. Therefore, we have a phase change, solid to a liquid. Our equation is still Q equals M, heat of fusion. We are given the Q and given the M, so we have some algebra to do. We plug those in and we get 134 joules per gram for our heat of fusion for copper. Okay, you can see how this value is different than our heat of fusion for water. Every substance is different. Next problem. This one goes back to one of the earlier types of problems we were doing in this unit. How much energy is used to heat a 25-gram sample of steam, so this is gaseous water, from 105 degrees Celsius to 120 degrees Celsius if our heat capacity, which is our specific heat, is C gas, for a gas, is equal to 2.02 joules per gram degree Celsius. Now, I didn't point out in this other one here. See, this is the number 2 is categorized orange. Number 3 is categorized green. If you go up here to my phase diagram, plateau orange, that's number 2. It's a phase change. Number 3 is a temperature change. We have to use a different equation. It's up here at the top of my phase diagram. So you can see how I reference that. And we scroll back down here. Okay, so my plan. I am going from water gaseous to water gaseous. What's changing is my temperature, so I write them above. Now, because I'm doing this temperature change, I want to mark my 120 is my final temperature, my 105 is my initial temperature. I am using my equations, Q equals MC, change in temperature of the gas. Now, of course, I don't necessarily have to say change of temperature gas in this problem because we're just sticking with gas. You'll see later on why it's important to specify what change in temperature I'm talking about. Just go with it for right now. Plug it in, 25 grams times 2.02 joules per grams degree Celsius times 120 minus 105. I've got to do that math. So that comes out to 15 times 50.5, and I get 757.5 joules. All right. Number 4, another temperature change. Water is cooled from 23.4 degrees Celsius to 4 degrees Celsius. If the sample was 99.8 grams, how much energy is released? Okay, the specific heat C value for liquid water is 4.184 joules per gram degree Celsius. Now, this one is a little weird. I'm going to set it up the same way, but I'm actually going backward on I'm going from right to left on my phase diagram. I'm going from warmer to cooler. So my plan is the same. I'm sticking with the water is liquid to going to water is a liquid. My temperatures are different though. I'm going from 23.4 as my initial to 4 degrees as my final. This just means that basically it's a little colder than, it's about this like 60 degrees room temperature maybe, down to like refrigerator temperature. So I've got a temperature change here. I'm using my Q equals MC change in T liquid. So here the important part here to see, and I'll do it in blue, is this part right here. Okay? My final temperature is 4, my initial temperature is 23.4, which means that I'm going to get a negative number, and that means that I am releasing energy. I've got a negative number here. So the energy we deal with is still 8,100 joules approximately, but we are releasing that. We see that because we have a negative number. Okay, so I think what we're going to do, I only get 14 minutes on these videos. So we're going to stop right here, and I'm going to put number 5's example on a new video. Okay? So, have a good day, and I'll see you on the next video.